Okay, welcome back everyone. In this video we're going to be talking briefly about the definition of a projectile, and we'll also take a look at how the one-dimensional kinematics equations that we learned last unit can be applied to two dimensions, so projectiles. So the definition of a projectile is just simply a moving object which is affected only by gravity. Okay, so it can't be rolling along the ground because then it's affected by the ground, and for the moment we're going to ignore any air resistance. But this means that things that have motors, things that fly because of air resistance, like frisbees, those don't really count as projectiles. Airplanes don't count because of their engines. So we're only talking about things that are moving through the air and are affected by gravity. So thrown footballs, baseballs, shells from tanks, all these are projectiles as long as they're only affected by gravity. Okay, and in order to analyze projectile motion, we need to start with what we already know. We already know that final velocity is equal to initial velocity plus acceleration times time. And we already know the distance equation, that a change in distance is initial speed times time plus 1/2 times acceleration times time squared. We already know this. So what we need to do is try to apply this to projectiles, so to the x and y directions. And usually what I try to do with this is to make a table that kind of highlights what's going on. And so in this table we're going to be looking at a couple of things. We're going to be looking at the horizontal motion, and we're going to be looking at the vertical. And we're going to be considering the acceleration of the object. We're going to be looking at the velocity of the object, and we're going to be looking at the position. Now, position is another word for displacement in a way. Alright, so now let's think about this. Based on our definition of a projectile, it's a moving object that's affected only by gravity. So we're told to ignore any air resistance. Now because of this, we can say that it has a vertical acceleration, AY, which is equal to gravity, which is equal to negative 9.8 meters per second squared, or downwards. Okay, so we can use a negative 9.8 for that. However, because of our definition, the horizontal acceleration, AX, by definition is 0. So there's no air resistance, there's no friction, there's nothing causing our projectile to accelerate in the horizontal or X direction. Okay, so now we can use our velocity equation and try to apply things to it. Now I'm going to stick on a bunch of subscripts for x and y, so try to follow along. Okay, so Vx final equals Vx initial plus Ax times t. Okay, so anything that could be split up into an x and y direction, I've put x onto it. Okay? And I'll do the same thing for vertical. So Vy final equals Vy initial plus Ay times t. Alright, now what does this actually mean? Because this isn't the equation that we'll end up using. Well, for the horizontal direction, we know what AX is. AX is actually 0 so this entire term is 0. And what we get is that Vx final is equal to Vx initial. That's important. What does that mean? Well, it means that if we have a projectile moving, it will keep a constant horizontal velocity. So it will always cover a constant amount of distance in a certain amount of time in the x direction. Now the vertical direction is a little bit different. We don't have 0 for acceleration. As a matter of fact, ay is equal to negative 9.8. And so the way that we're going to write this equation is Vy final is equal to Vy initial plus g times t. And we're just going to say that g is negative 9.8. Okay, so just remember that. And we're saying by definition that downwards is negative and upwards is positive. Okay, so far so good? You're supposed to say yes. Alright, so now we move on to position. And for position, we start with our general equation that delta D is equal to V initial t plus 1/2 AT squared. Again, I'm going to change things a little bit. I'm going to say delta dx equals Vx initial times t plus 1/2 ax times t squared. Likewise, delta dy equals, ready for this, Vy initial times t plus 1/2 ay t squared. As a matter of fact, let's zoom in just a little bit on this. Okay. So there's position. We'll do x position first. So sometimes for x position, instead of delta dx, we can just write this as delta x. Okay? Vx initial times time. And remember what we said ax was. Ax was 0, so that whole term is gone. And this is our whole equation. Likewise, this. Okay? Now we go over to the y position. Okay? So instead of delta dy, we can say delta y equals Vy initial times time plus 1/2 g t squared. So this is our equation for the y position as a function of time. Okay, so now let me zoom back out. This is pretty much all you need to know about projectiles. If you understand this chart, and by that I mean you know how to use these equations, then you'll know everything there is to know about projectiles. So in the following videos, this is video 19, at least for right now. In the following videos, I'll give some examples of solving projectile problems.